Ever wondered how a semiconductor controlled rectifier, or SCR, is constructed? This intricate three-terminal device, also known as a thyristor, is a key player in the world of power electronics. Acting as a controlled switch for rectifying purposes, the SCR is constructed from three layers of semiconductor material, P-type and N-type. So, how does it all come together? Let's start from the very beginning. Firstly, we have the anode. This is where the current enters the SCR. Made of P-type material, it acts as the positive terminal during forward biasing. Secondly, we have the cathode. This is where the current exits the SCR. Composed of N-type material, it serves as the negative terminal during forward biasing. Lastly, there's the gate. This third terminal is what controls the switching of the SCR. It is the gatekeeper, so to speak, responsible for turning the SCR on or off. The gate is insulated from the main current-carrying terminals, keeping it separate and independent. These three layers form two PN junctions, P1N and P2N. The central region, made of P-type material, between these junctions is known as the P-base, or P-layer. But how does an SCR work? Well, the operation of an SCR involves different modes: forward blocking, forward conduction, and reverse blocking. In the forward blocking mode, the SCR starts off in a state where the anode is at a positive potential and the cathode at a negative potential. This makes the P1N junction reverse biased, preventing current flow between the anode and cathode. The SCR stays in this state until a voltage is applied across the anode and cathode, exceeding the forward breakover voltage. Then we have the forward conduction mode. When a sufficient forward voltage, greater than the breakover voltage, is applied across the anode and cathode, the P1N junction becomes forward biased. Once triggered, the SCR enters the forward conduction mode, allowing current to flow from the anode to the cathode. This conduction will continue until the current drops below a certain threshold or until a reverse voltage is applied. In reverse blocking mode, the SCR can block reverse voltage when the anode becomes negative with respect to the cathode. This reverse bias is the P2N junction, preventing the flow of current in the reverse direction. Finally, there's gate triggering. The gate terminal is used to control the turning on of the SCR. Applying a positive pulse to the gate triggers the device into conduction. However, the gate signal should only be applied when the SCR is forward biased, and it must have sufficient amplitude and duration to overcome the forward blocking state. Semiconductor controlled rectifiers have found their places in a wide range of applications. From power control circuits and motor drives to voltage regulators, all these systems require controlled rectification. Understanding the construction and working principles of SCRs is crucial for their efficient and reliable operation in diverse electrical circuits. So there you have it. The construction of an SCR demystified. Remember, it's all about the three layers, the anode, cathode, and gate, and the various modes of operation: forward blocking, forward conduction, and reverse blocking. These are the elements that make an SCR what it is. Until next time, keep exploring the fascinating world of electronics.